We're going to take a look at something called rectilinear motion. It's pretty easy. It's just based on stuff we've already done. So we take the ideas that we've already talked about, which is the fact that if you take the derivative of, what's up, tardy boy?
Have one?
Have one what?
That worksheet one? Sure. Thank you.
I don't
Thank you.
So we're going to base this off the idea that if you take the derivative of the position function, you get the velocity. If you take the derivative of the velocity, you get the acceleration. And then going backwards, the antiderivative of the acceleration gives us the velocity, and the antiderivative of the velocity gives us the position. Okay. So we're going to look at a special type of motion, and that is, and there's a couple different varieties, but it's something moving on a straight line and going back and forth. Okay, so for instance, a weight on a spring bouncing up and down, a particle in a magnetic field sliding back and forth on an axis. Okay. The problem is we can't accurately represent that in a graph, so we do something called a schematic to represent the motion. Okay, so for instance, if I have a particle that starts here on some axis, and it starts moving forward, then turns around and goes backwards, and then moves forward and goes backwards, and then ends up right there, you can see that that's not a really good picture of what's going on. By the way, we've talked about the difference between total distance and displacement, right?
Yeah.
Okay, what's the difference here? Which one's bigger?
Total distance.
Total distance, good. And we'll talk about the math involved in that. So instead of representing the motion this way, we're going to elevate the particle and demonstrate or describe the motion using something called a schematic. Okay, so even though the particle isn't actually traveling along that path, it gives us an opportunity to look at what kind of path it's taking. So it goes down a certain distance, turns around, comes back the other. It doesn't really turn around; it just goes the other way, then comes back the other way. Okay. So we're going to use the idea of the derivative and the integral to represent this equation, or this particle, I should say. Okay, so let's see what we got. A couple things. What is the difference between... It's not Mary, it's me. I'll let you know when it's Mary. What's the difference between these two things? That just solicited an oh.
One can be positive.
Greg?
Is one of them the total distance and one of them is the displacement?
Not yet. We'll get back to that in a second. Raj?
Is the one with the absolute bar speed?
Yes, correct. What's this one? Velocity. What's the difference? Raj?
Speed can't be negative. There's no change in direction.
Velocity has to do with direction, whereas speed is always a positive value. Okay, so speed-wise, if you're going backwards in your car at 40 miles an hour, you're still going 40 miles an hour. Velocity would be negative 40 miles an hour. Okay, and then we had the relationship here that S prime of t is equal to v of t, because of type. S double prime of t equals v prime of t equals the acceleration. And again, that's stuff that we already know. And so your first example, that's not your example. I got this example. Let's start with this. I've got a position function. So maybe find some space to take some notes there. T cubed minus 12t squared plus 36t minus 20 is a position function for some particle moving along an axis. And you're going to be asked to describe the motion of that particle on the interval from -1 to 9. So what does it do? What direction is it traveling at one interval? Where does it turn around? When is it going the other direction? That kind of stuff. So we need to do two things. Take the derivative and then take the derivative. Excuse me. All right, what's the derivative? Who is it? Who's talking?
3t squared minus 24t plus 36.
Uh-huh. And what's the derivative of that puppy? Go ahead, Amanda, you're on a roll.
Oh, okay. 6t minus 24.
Excellent. Okay, so what do we care about? We care about where the velocity is equal to 0. Why? What was that, Greg?
But
You
on
just
top of this.
change your mind in a way? Luke, what do you got?
It's changing directions.
Good. It's the point where it changes direction. So the velocity slows down, reaches 0, comes back the other way. So we need to get some data organized here, and I find the easiest way to do this would be to organize it into a t-chart. So I'm going to do t, and I'm going to do s of t. And I need to do a couple things first. I need to figure out where the velocity is equal to 0. So take that velocity, set it equal to 0, and solve for t for me, please.
T is equal to 2 and 6.
Can somebody confirm?
Yeah.
2 and 6, beautiful. Okay, so those are our relevant points. Where's it starting? Where is it ending? Where is it changing directions? By looking at the values where the velocity is equal to 0. Now I need the position function. You can find the position function a couple different ways. You can manually sit there and type in -1, 2, 6, and 9, or you could put that into y1 and look at a table. You could do it a bunch of different ways, but I need to know where is it at -1, 2, 6, and 9. Go ahead. And I would suggest you use your calculators. Now, I just rattled off a couple ideas. Do you all understand what I'm saying about that? How to do that? So you know how to store -1, type this into the home screen, hit enter, spits out an answer. Then store 2, go back to that function, do it again, or put this into y1, and then go to your table, and just look at what the values are right off the table. It's entirely up to you. I don't care. Let's go to your pipe. Ready? Not afraid of you. Maybe a little, but I'd bring some friends. Okay. Somebody else? Wait, you did your share.
Okay, sorry.
I've got a whole table of them.
Woo! Getting all fancies in your pantses. What's 2?
0.
Yes?
How do you get to the table?
6? Did you ask a question? I'm sorry.
Yeah, how do you get to the table?
It's tablet. It's over here somewhere. Good.
Are you asking for VT or SFT?
I'm asking for S and T. What are you doing?
Yeah. That 63 is not right either. Because I got 63.
Yes, it's not right?
It's not right.
It's not right.
Can these be negative or did I do this wrong?
Well, they can be negative. Yeah.
Okay.
Yeah.
Yeah, -69 is one.
All right, let's start over. Connor, what's -1?
-69.
Yeah.
People agree with that one? Keep going. What do you got for 2?
12.
Good.
Good.
-20.
You seem to be onto something.
Let's go, Connor.
61.
Okay, beautiful. Now I need to put that together into a schematic. So what's happening? At t equals -1, the particle is at a position labeled as -69. So it's a position, it's not a speed or anything like that. So think of it being on a number line. It's on the x-axis. Where is it at -1? It's at -69. And then it starts moving which direction? Up. So we're going horizontal. Yeah, to the right. It gets to gets to 12, and then what happens? Goes back to negative 20, then turns and comes back to 61. So negative 1 and 9 are my starting and ending points. 2 and 6 are my turning points. And I need some space here, so let me get rid of this. We'll come back to that. We'll leave those there. And so schematic will look something like this. Start with a nice long number line.
Oh, I was drawing it.
Mary,
Sorry.
what just happened there? Okay, we're going to start here at negative 69. Put a big honking dot there. That's at t equals negative 1. So the distance goes on the number line. The time goes near the function. It's going to go all the way over here to 12. So I'm guesstimating where 12 is. And so this is going to go this way and then turn at 12. Okay, where's that happen? T equals 2. Then it goes back to negative 20. Let's put it right there. Oops, that should be that. And that happens at t equals 6. And then it ends all the way up here at 61 when t equals 9. I'm missing one thing, and that's arrowheads. To show the direction of travel, we want to put arrowheads on there. And we're done. What happens at t equals 4? At t equals 4, the velocity is negative. How do you know that? Okay. What else?
You start at -1, you start off going forward, positive, and once you hit 2, it's back.
Mm-hmm.
And then at 6, you're back positive.
So why did I ask about t equals 4 specifically?
I think it's right in between 2 and 6.
Look at that. What happens when t equals 4?
Acceleration,
Good. Which means what? It stops moving?
it's locked down.
At a constant speed.
Good. When the acceleration is 0, then the speed is constant. And I'm sure you've all had physics, so you know that if there's no acceleration, you can't, you know that business, right? Where if you're in a closed box, you're traveling at a constant velocity, there's no way to know that. Did you not learn that in physics? If you're in a closed box, so no windows, and you're traveling at a constant velocity, no acceleration, that there's no experiment that you can do that proves that you're moving at all.
That makes sense.
Yes?
Yeah.
Why are you looking at me like I'm speaking Italian?
Because you are.
No, Italian's more
Buongiorno.
understandable than what you just
I
said.
understand.
It's like you do it to yourself.
Right, it has to do with, it's a little snippet of relativity there, that there's nothing that indicates that you're moving. So like right now, you're moving, right?
Definitely.
You know that, right?
Yes.
Because the Earth is spinning, and the Earth is moving around the sun, and the sun is moving around the galaxy, and the galaxy is moving around the universe.
Stop.
What?
I'm staying right
Bad timing. So if the acceleration is 0, there is no way that you can verify that you are moving. So in other words, if you're in your car with the cruise control set at 50 miles an hour, it doesn't matter what you do. It's just going to act like if you're standing still. And you throw a ball up, you catch it. You throw a ball up, you can catch it. That happens. When you start to accelerate, that's different. If you're in the car going from 0 to 60 in 2 seconds and you throw a ball up, it's going to end up in the back seat. Kind of. What's that?
There's no back seat in cars so fast.
I just threw out some numbers.
It's really fast.
I understand. So that point happens right there, where t equals 4. for our purposes, that doesn't really matter. We don't really care about that. We're more concerned about the schematic of what's happening with that graph. So we're going to be looking mainly at the position function and the velocity function. Okay? That's it. Rectilinear motion. Rectilinear motion just means it's traveling along a axis. It could be horizontal, it could be vertical, it doesn't matter. The other thing that I wanted to mention is going back to some of the problems we did where we're throwing objects up in the air or dropping objects. Okay. So, for instance, throwing a ball up in the air off a cliff and calculating how long it takes to hit the ground. That kind of stuff is still using that formula that we've talked about before, the 1/2 AT squared plus V naught T plus S naught.
Sure.
Yeah.
Ooh, that was weird. I don't know.
It was filled with sausage.
Right? Are we good? Okay, good. Question?
Are we ever gonna have to say the difference between the total distance and,
Excellent question. So now I've done a schematic here. Everything's said and done. What's the total? Let's start with the easy one. What's the displacement?
How far you are away from your original?
What's the numerical value of the displacement?
108-ish?
No?
130.
130. Started at -69,
Oh.
ended at 61. That total, that displacement then is 130. What's the total distance, however? So for total distance, I'm assuming you're adding up all those little legs, right? So you'd have to do -69 to 12, 12 to -20, -20 to 61. Total distance would be bigger.
170. Yeah, on the dot.
So if the schematic gets very complicated, that's too much work. So we can use a little snippet here, and that is the following chunk of information. If you take the antiderivative of the velocity, you will get the displacement. Displacement. If you take the antiderivative of the absolute value of the velocity, you will get the total distance. That's most likely going to be helpful when you're doing Fn int, because realistically speaking, we haven't done a lot of, in fact, I don't know if we've done any integrals involving absolute value. So for instance, with your calculators, Fn int, the velocity, from -1 to 9, and then Fn int, the absolute value of the velocity from -1 to 9. And look at your answers. Do you know how to get the absolute value? Easiest way is to go to the catalog at the bottom.
I go back, scroll over one.
Whatever works for you. Okay, so our displacement, we should get 130.
Yeah.
Go second, see the catalog there? So go second catalog. It's the first one. So somebody did the displacement?
Yeah.
130?
Yeah.
Awesome. And then our total distance should be those numbers that people were spouting out before that I wasn't really listening to.
194.
What is it?
194.
194.
I got that.
193.
Was it erased?
No, you didn't think it was right. And he.
No, I got a really small number.
Okay, we good?
Okay, you guys check that.
That's all I got for you.
Oh, man.
Wait.
So tomorrow, we'll spend some time. Let me check my calendar too, because we might have, I don't think I have any more application of derivatives for you for tomorrow, for tonight I mean. But tonight you have those 4 schematic problems that I gave you. Bang those out. And then, give me a second here, let me stop this recording.
Do you want us to?
Can I erase this, by the way?
Yeah.
Okay.
Do you want us to